All right, so let's look at 10.2 series. So series is very much like sequence. So sequence is a list of numbers, and when you add them all together, that becomes a series, right? So I'll give you a quick example. Let's say I have 1, 2, 3, 4, 5, right? A finite sequence, and the series would just be the sum of those 5 elements, right? So that's just 1 plus 2 plus 3 plus 4 plus 5, which is what? 15, right? And that's it. That's series, right? But what we're more interested in is infinite series, right? What happens when you add up infinitely many numbers in the sequence, and then is there a sum, right? That's the question we are interested. All right, so a quick example would be like this, right? We're adding up infinitely many numbers, and then right here, what we have here, that is your formula for the nth term, right? So another notation to represent infinite series is this sigma notation, right? We want to add up uh, all the terms in the sequence from 1 to infinity, and we want to see what that is. And sometimes we don't want to add up everything. We just want to maybe take the first few terms, right? For example, 5 terms, or in this case, n terms. So this notation, capital S sub n, represents the sum of the first n terms, and it's called the nth partial sum, right? Partial sum. It's not the infinite sum, right? So what we have earlier, let's say 1, 2, 3, 4, 5, 6, 7, and so on, right? The natural number sequence, right? And if we just look at S5, means we want to look at the sum of the first 5 numbers, right? So it's just 1, 2, 3, 1 plus 2 plus 3 plus 4 plus 5, which gives us 15, right? That's an example what we have. All right, now the example from earlier, we have this infinite series, right? Adding up all the terms in the sequence of an, right? And here we worked out the first few partial sums. For example, the first term is just 2. S2 means adding the first 2 terms. We get a over 3, and so on, right? So the partial sum of the form, it's the when you use the partial sum and put them in the sequence, you get 2, right? A third, 26 over 9. And then the S4 would be 80 over 27. And then if you keep going on, then we can build a table like this. As you can see that when we add the first 25 turns, we get 2.999999, which is very close to 3, right? So if we can come up with a way to find out what the infinite sum is, right? For example, in here, it looks like it's approaching 3, right? So maybe we can say that, okay, the infinite sum is going to be 3, right? But we don't have time to, go through all the work and adding everything together. So this is what we're going to be doing in this section, is that first, is there a sum? Or I should say, is there a finite sum? Right? And 2, if there is, what is it? Okay, and that's what we're going to focus on in this section. All right, so it's very similar to what we're doing sequence for now, but in this case, we are actually looking at the sum, see if we add up infinitely many terms in the sequence, do we get a finite number, right? So we call this small s, lowercase s, the sum of the infinite series, right? And the series is called convergent if there is a finite number that we can represent for the sum. Now, if we can find the value of s, then the series is called convergent, right? If the value S does not exist, then we say that the series is divergent. Okay, so convergent if we can get a value of S for the sum. If not, then we say it's divergent. Now this notation in the beginning right here is capital S sub n, remember from earlier, it's the sum of the nth term. Right? So what we're taking here as n approaching infinity is we're actually looking at the infinite sum, and if we can get a value out of it, then it's called convergent. Right. The first type of series that we're going to talk about is called the geometric series, and each term is obtained by multiplying the previous number by a common ratio r. Right. So, for example, let's say we have an is 2r to the n. Let's say. Let's just make it a little easier. Let's say 2 to the n, right? All right, so this will look like what? 2, 4, 8, 16, and so on, right? Now, of course, you can see that it's actually increasing nonstop. So when you add everything together, it's going to be infinite, right? So for geometric series, this only converges for a certain value of r, right? Now let's take a look at some examples. All right, for r equal to 1, right, then our sequence will look like this: r times 1, a times 1 to the nth power, right? So when you add up the first n terms, you get a, right? That's the first one, plus a, plus a, plus a, and so on, right? So it's actually going to be n times a, right? Because you're adding up n of them, right? Now, as n approaches infinity, this is gonna go to infinity, right? Therefore, we can say that it diverges when r is 1. Now, when r is -1, we get divergent as well, but for a different reason, right? Let's see. All right, so if the sequence is a times -1 to the n, so that looks like negative a, negative a, and so on, right? That's the sequence we're looking at. And when we add up the first n of them, we get negative a plus a minus a plus a, dot, 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 and so on, right? But it's very hard to know how many we have because each pair of negative a and a, that gives us 0. So it actually depends on how many a's we're adding, which means this is going to turn out to be -1 to the n minus 1 power of a. Okay, now the -1 here, it's going to take care of the signs, right? Because we started with a -1, right? But the second one, a2 is going to be subtracted, cancel out the first one, right? So we will have this n-1 term here. And if you take the limit of this to infinity, right, it's actually, it actually does not exist. Does not exist as n approaches infinity, right? Because it's oscillating between negative a and a, going round and round, right? So it's not going to make sense when we take the infinite sum. Now we actually saw something like this in 10.1, right? If the ratio is between -1 and 1, the sequence converges to 0. If r is 1, then it converges to 1. Everything else is going to be undefined or infinite, right? So this is going to help us with our case here as well when we want to add everything together. So for geometric series, the series is going to converge, convergent if R is between -1 and 1. Now, notice I'm not including 1, right? Because we know that the sequence for R to the n, if R is 1, then we get a sequence of 1s. But when we add all 1s together infinitely many times, we still get infinite, right? So in that case, it's going to be convergent, right? So geometric series is convergent if R is strictly between -1 and 1, or if the absolute value of R is less than 1, okay? And the sum, the infinite sum, has the formula a over 1 minus r. Okay. Now, if you're interested in how we get this, in the textbook, they actually show you all the steps and how to derive using partial sums and taking limit to infinity to show that the sum of a geometric series actually comes to this, a over 1 minus r. Furthermore, we also have a formula for partial sum of the geometric series, which looks like this: a times 1 minus r to the n over 1 minus r. Right, so the main difference between these two is this is the infinite sum. Okay, and this is partial sum. Okay, so if you just want to add up the first few terms of the geometric series, then you would use the partial sum. But if you want everything, you would use the infinite sum formula. As you can see, the infinite sum formula is much easier than the partial sum formula. All right, so let's take a look at some example. All right, so this was the example that we are looking at earlier, and we saw that on the table that the sum actually is approaching 3, right? 2.9999. And here we're going to show that whether the series is actually 3. Okay, so let's see. We can first factor out the 2, so we have 2 times this infinite series right here. All right, so the infinite sum formula is a over 1 minus r, right? So a is the first term, right? Term. And r is the ratio between terms. Okay, so in this case, a is going to be 2, right? Our first term. Or you look at here is 2 times 1, which is 2, right? And r is what do you need to multiply to get to the second term, right? So from 2 to 2/3 to 2/9, or if you can look at on the right-hand side inside the parentheses, we can clearly see that to get to the next term, all we did was multiply by 1/3, multiply by 1/3, and multiply by 1/3, and you can see that we actually have this right here, and that tells us what the ratio is, right? So it's 1/3. To be a little more specific, this term right here is actually 1 over 3 to the power of n minus 1, right? So by looking at this, we can say that, okay, the ratio is 1/3. Now, r, 1/3, is between -1 and 1. In a geometric series, we know that it's going to be convergent. We know it's convergent. Okay, so now that we know it's convergent, we just need to find the sum. And to find the sum, we can just use the formula from up here. S is equal to a over 1 minus r, which is 2 over 1 minus 1/3, which will be 2 over 2/3, which comes out to be a 3. Okay, therefore, this is your infinite sum. Okay, and it's convergent. Right? Very easy, right, for a geometric series. So in cases like this, you have to identify whether you have a geometric series or not, because geometric series is one of the series that is very easy to work with. We know a lot about them, right? We know when it's convergent or when it's divergent. And once we know it's convergent, we have a very simple, nice formula to find its sum. All right, so here we have a really fun example. So we have a big square with sides 1 and 1. So the area is 1, right? Now, what we have here is we cut the square into half and half and half and half infinitely many times. So when we add up the areas, A1 plus A2 and so on, the infinite sum of the half of the area of what's left, it should be equal to 1, right? So let's check that. Let's see if it's actually 1. Okay? So let's write out the series first. So the sequence, let's write out the sequence. So A1 is going to be 1/2 of the square, which is 1/2. And then A2 is going to be half of the previous one, which is 1/4. And A3 is going to be half of the previous one, which is 1/8, and so on, right? So what we're looking at is we want to find the infinite sum of all these little areas, right? Starting from A1, A2, and so on. So it's 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot, 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 dot. Okay, so it's an infinite series. So let's see if we can identify the terms that the values that we need for our infinite sum, which is a over 1 minus r, right? So a is the first term, right? 1/2, right? And then r, the ratio, right? To go from the first term to the next term, we multiply by 1/2, and then by 1/2, and so on, right? Okay, so r is going to be 1/2. So what we have here, by plugging everything into the formula, we get 1/2 over 1 minus 1/2, which is 1/2 over 1/2, and that gives us 1. Okay, and it matches with our original assumption here, right? When we add up all the squares, we actually get 1. Now, the same idea can be applied to drinking, let's say, a glass of something you like, right? All right, we have a glass of, let's say, orange juice, OJ, my favorite, right? And let's say this, each time you take a sip of your orange juice, you are always drinking 1/2 of it. All right, after one sip, you have 1/2 left. And then after the second sip, you have half of whatever is left right here. And then you take infinitely many sips. At the end, how many cups of orange juice have you drunk? Right? And you can see just by looking at the picture, you only have one glass of orange juice, right? So the answer is 1 cup of orange juice. A similar idea to what we are doing here with the area of the square. Now, another technique of a geometric series is we can actually convert repeating decimals back into a fraction, right? So we want to represent 2.15 repeating as an improper fraction by using a geometric series. Okay, so let's do this. So 2.15 repeating means I'm looking at 2.1515151515151515. You might be wondering how many times we're going to do this, but I'm just going to stop there. Actually, we're just going to look at the first 6 digit like that, right? So I'm going to write this out using fractions, right? So first is 2 plus 0.15, that's 15 over 100, right? That's the first pair of 15 right here, okay? And the second pair of 15 can be represented as 15 over 10,000, okay? And maybe you can see what we're doing here. And the third pair of 15 can be represented as 15 over 1 million, right? 6 zeros. Yep. And then we can move on, right? So the next thing is the numerator, we have the same thing. And then all that changes is the denominator, okay? So what we're going to focus on is starting from here to infinity. We're looking at this as an infinite series, okay? All right, so let's see if we can come up with the infinite sum of this, right? So again, S is A over 1 minus R. Well, it's very easy to identify our A is 15 over 100. Okay, what about the ratio? To go from the first term to the next, we multiply by 1 over 100, right? Same thing from here, multiply by 1 over 100, right? And so on, right? So our ratio is actually 1 over 100. And by geometric series, we know that R is between -1 and 1. So we know this is going to be convergent. So let's see what the sum is. So sum is equal to A, 15 over 100 over 1 minus 1 over 100, which is 15 over 100 over 99 over 100. That comes out to be 15 over 99, which can be simplified to divide by 3, so 5 over 33. All right, so what we have just shown here is that this whole thing in the bracket, right, this whole sum is equal to 5 over 33, right? So what we can do now is we know 2.15 repeating is just 2 plus 5 over 33, which would just be 66 plus 5 over 33. So that would be 71 over 33. Okay. Now, of course, with the calculator, you can always check if you have repeating decimals, how do we go back to an improper fraction? And this is how you do it. This is how the calculator does it, right? So it's a really fun little technique that I don't think you guys have seen before, but this technique is quite fun and gives you a lot of practice for geometric series. The next type of series we're looking at is called the telescoping series, which is when the middle terms cancel and the sum collapse into just a few terms, right? So here we have an example, infinite sum of 3 over n times n plus 3. And we can actually do partial fraction decomposition and then break it down as 1 over n minus n plus 3. All right, so let me show you what we're talking about here. I'm just going to write out the first few terms. All right, so we have 1 minus 1/4 plus 1/2 minus 1/5 plus 1/3 minus 1/6 plus 1/4 plus minus 1/7 plus 1/5 minus 1/8 plus 1/6 minus 1/9, and I'm going to stop there. Okay, so you can see that we have negative 1/4, positive 1/4, negative 1/5, positive 1/5. So all these are going to be reduced, right? Like that. And then negative 1/6 and 1/6, and so on and so forth, right? So a lot of the terms are going to get canceled out. And then I think eventually you are going to get negative 1/7, right? With the next one, negative 1/8, and negative 1/9, and so on, right? So a lot of the terms are going to cancel out. And let's look at the nth term. Right? So let's say I have term, it's going to be plus 1 over n minus 2 minus 1 over n plus 1. Right, that's the n minus second term, plus 1 over n minus 1 plus 1 over n plus 2. That's the n minus 1 term, plus 1 over n minus 1 over n plus 3, and so on, right? So you can see that if we are just looking at infinite sum, all these are going to, with the n in the denominator, they are all going to 0, as n approaches infinity, right? So the only terms that's going to matter is the one that's remaining, right? The 1/2, the 1/3, right? So we can actually simplify the sum of telescoping series down to just 1 plus 1/2 plus 1/3. The terms that are not getting canceled, they are not getting reduced, which gives us 11 over 6. Okay, so that's what a telescoping series is. And let's look at a few more examples. So I'm going to show you a slightly different technique to find the sum of telescoping series. Right, so here is our telescoping series. Well, we don't know if it's telescoping because we have to show whether it cancels out or not. All right, so the first thing is we just want to look at a partial sum of the n terms. Right, so that's why the first few ones. So starting with n equal to 1, that's 3 minus 3/4 plus 3/4 minus 3/9 plus 3/9 minus 3/16 plus 3/16 minus 3 over 25, and so on, right? And then we'll get our n minus 1 term, which is 3 over n minus 1 square plus minus 3 over n square plus 3 over n square minus 3 over n plus 1 square, right? So that's A1, A2, A3, A4, an minus 1, and an right here. Okay, now let's see if anything cancels out, right? So we have negative 3/4, positive 3/4, negative 3/9, positive 3/9. So you can see that A1, A2, the adjacent terms are canceling each other out. Negative 3 over 16, positive 3 over 16, and then the negative 3/25 is going to cancel with the other one, and then so on and so forth. This one is going to be canceled out, and then the last one we're going to simplify, reduce the negative 3 over n squared and 3 over n squared. So what does that leave us? All the middle terms are canceled out, leaving us just the first term, the 3, and the last term, which is 3 over n plus 1 square. So this is just the partial sum, right? In order to find the sum, the little s, we just need to take the limit as n approaches infinity, right? This is the partial sum. If we want the infinite sum, all we need to do is take n approaches infinity of Sn, which is limit as n approaches infinity of 3 minus 3 over n plus 1 quantity square. Now, the second term right here, that's going to go to 0, right? Because we have n in the denominator, leaving us just a 3 as our limit, okay? So another way that you can think about this is in the sum, the only term that is not getting canceled out is the first 3 right here. Everything else, if you keep going on, is going to cancel out each other and nonstop, right? That's why we can get the infinite sum is equal to 3. All right, now before we move on to our next topic, I just want to introduce you to some logic. Okay, So let's say if A implies B, right? So in notation wise, we just do A arrow B, right? If this is true, right? So let's say a good example. Let's see, right? Let's say if you win the lottery, that implies that you bought the ticket, right? I mean, that's pretty obvious, right? If you won the lottery, that means you spent some time to buy the ticket. Right? But we want to talk about a variation of this. The first is converse. Converse of A implies B is B implies A. All right, or B implies A. So the converse of this statement, win the lottery, means you buy a ticket. The converse would be that you bought the ticket and you win the lottery. Now, is this always true? No, right? Most of the time you don't win, right? So this is a false statement. We cannot say that if you bought a ticket, then you win the lottery. Then everyone else would buy the ticket, right? Why not? Then I don't have to work, and you don't have to go to school. No, I mean still stay in school even if you win the lottery, right? So the key here is that converse of a statement is not always true, right? However, what we're more interested in is something called contrapositive. So contrapositive of the statement A implies B is not B implies not A. Okay, contrapositive of A implies B is not B implies not A. So in the example of a lottery ticket, it means if you didn't buy tickets, means you didn't win the lottery. I mean, that's obvious, right? If you win the lottery, that means you bought a ticket. If you didn't buy the ticket, that means you didn't win the lottery. Now, contrapositive is always true, or that is based on if your original statement is true. All right. So if A implies B, then not B will imply not A. Okay. So the idea of talking about this is to talk about our next topic, but take some time and understand what we're talking about here. If you have a statement A implies B, right, you can use the example here, or another example that I use is with test and study, but sometimes that doesn't work out. Okay, so if you win the lottery, that means you bought tickets, right? That's true. We can all agree on that. Now, the converse is not always true. Converse means you bought ticket and you win the lottery, right? This is not always true. But the contrapositive is always true, right? If you didn't buy tickets, then you didn't win the lottery, right? So contrapositive is always true. Now, we are going to take this and use it in our class in terms of convergent and divergent. Okay, so this is our statement. If the series infinite sum of an is convergent, then limit as n approaches infinity of an is 0. Now that's true, right? If your sequence at the end of your sequence is 0, that means your when you add everything up, it's going to be convergent, meaning it's going to go to some value. Now the converse will be if your limit goes to 0, then the series is convergent. Now this is false, right? Here we have an example, right? 1 over n. 1 over n actually, if you look at the sequence, when you take n to infinity, you actually get 0, right? You get 0, right? But the series actually diverges, right? It's one of the geometric series that diverges. Okay, so converse is false. But what we're more interested in is the contrapositive, which gives us a very nice property. So the contrapositive is also something we can use called the test for divergence. If the limit of the sequence is not 0 or does not exist, then the series is going to diverge. Now this is true, okay? Now what we can do here is we can use this test for divergence to check if a series is divergent. Now notice that, remember, this is only for divergence. Does not check for convergence. Okay, and let's do an example. All right, so here we have an infinite series, 3n squared over n times n plus 3. All right, we have some of the terms here, and we're going to check if this diverges. Right? To do this, all we need to show that is that the limit of an is not equal to 0 or undefined. Right? So let's say the limit as n approaches infinity of 3n squared over n times n plus 3. Now we can actually distribute the denominator, and we get limit of 3n squared over n squared plus 3n. So same thing, same degree polynomial, so this is gonna go to 3, which is not equal to 0, right? Remember, for test for divergence, we want to show that it's not equal to 0. Now we have shown that it's not equal to 0, we can say that by test for divergence, the series diverges. Okay, that's what the test of divergence do. If when you take the limit of an is not equal to 0, then we can say that the series is going to diverge. Now, here is one little thing that you have to be very careful of when you are doing tests for divergence. Let's say if you're doing tests for divergence and you do get a 0. So if you get a 0 for the limit, you cannot conclude that the series converges. It just means that it has a chance to converge. So if you're doing tests for divergence and then you get a 0, it means it's inconclusive from test for divergence, right? And in that case, you will have to move on to some other test to check if it diverges or converges. So be very careful. The test for divergence only checks if your series diverges. If the test of divergence fails, then you cannot say anything about the series. If the test of divergence fails, you cannot say it converges. It just has a chance to converge, but it does not necessarily have to converge. Okay, so be very careful. And actually, let's look at one example where that happens. So the one that we're talking about, right? 1 over n. Right? So this series actually diverges, but when you take the limit as n approaches infinity of an, that's actually equal to 0, right? So if it's 0, it's inconclusive. Right, so you will have to use other test to show that this diverges. All right. And then we'll actually show that the infinite series of 1 over n diverges in the next section in 10.3. In 10.3. All right, last thing from 10.2, if we have two convergent series, and then the scalar multiple of any of the series is convergent as well. And also when you add or subtract convergent series together, they are convergent as well, right? You're just adding or subtracting two convergent series. All right, so one example would be like for the first one, all right, let's say we have 7 times 2 over 3 to the n minus 1. Right? And we saw that this the sum of this is 3 from earlier. And so what we can do is we can bring out the 7 to the outside, like that. And then the infinite series, now this whole thing is equal to 3, so it's just 7 times 3, which is 21. Now, same thing with the adding or subtracting, right? You can break them up into two separate infinite sums, and then add the sum or subtract the sum as you wish. Okay. All right. And just keep in mind that the sigma notation, it just means you're adding a bunch of numbers together. Okay. All right. And that's it for 10.2. And I'll see you guys soon.